Welcome to our IMTC WebRTC webinar. My name is Henrik Gisch. I'm your moderator today. Let me quickly cover a couple of housekeeping items. First of all, we will record the webinar and provide access to the recording later on. And secondly, while the speakers present, I will mute everyone else. At the end of the meeting, there will be a Q&A section. And I remind you to unmute yourself in case you want to ask questions. And you can do that either in the client by pressing the unmute icon, or in case you dialed in, please press *3. So now let's kick it off. And first of all, let's have a look to the agenda. We have great topics with outstanding great speakers today. First of all, Andy Hutton and Alex Bouillard are going to talk about standards and implementation status of WebRTC. Andy is head of standardization at Unify, and Alex is principal architect at Citrix. Next is going to be Alex from Video. He's chief scientist, and he is going to talk about what's next for video in the WebRTC space. Finally, Bernard Aldoba, Microsoft. He is principal architect. Is going to talk about WebRTC object models in WebRTC 1.0 and in RTC. Again, at the end, there will be a Q&A session, but now let's start. And Andy, please take it from here.
Yeah, so actually, contrary a little bit to what Jan says, I'm actually going to present a few minutes about an introduction to the WebRTC interoperability activity group in the IMTC. The IMTC is organized into a number of activity groups. I'm not sure how many there are at the moment, 10 or more, around various different technologies. So we're talking here about WebRTC, obviously. Next slide. So the WebRTC activity group in the IMTC is focused basically mostly on enterprise use cases, although I would say not exclusively. We also provide a forum for I would say IMTC members to share information. We develop interoperability use cases, and we run interoperability test events. A lot of you may have heard or even attended the IMTC SuperOp in the past. And certainly we had quite a bit of WebRTC stuff at the last SuperOp in May last year. We intend to provide input to standards organizations where we have the expertise to do so. And we're currently looking at developing a WebRTC implementation scorecard, where we look at detail of what WebRTC browsers are implemented and actually start to maybe test them and score them against each other. Okay, next. So this is just actually a diagram from the IMTC SuperOp last year. One of the things we do during the SuperOp is we connect all the equipment in the room together, or as much of it as we can. So that's all the video endpoints, MCUs, etc., mobile handsets, whatever we have, into a massive conference. And last year we had a sprinkling of WebRTC enabled devices and MCUs around. So that's what the red circles show there. Maybe there'll be more this year. Okay. So what are we doing? What do we think the WebRTC activity group will do in the future? Certainly, WebRTC is still an exciting place to be. I think, especially this year, quite excited about this year in the fact that we're moving towards WebRTC 1.0 being complete and seeing a lot of standards compliant implementations in browsers. And IMTC can play a role in testing those out, etc. And we'll also starting to talk more in the standards organization about WebRTC next version, what we're calling WebRTC NV. And certainly video, things like Simulcast, well, Simulcast might be in 1.0, but Simulcast and Scalable codecs will be a component of, or expect a component of WebRTC next version. So we see some opportunities, for our IMTC activity group. Certainly video is the center of WebRTC innovation at the moment. I think things that are going on in the standards world, especially around the codecs, simulcast support, SVC support in the future, etc. And that's an area where IMTC members have a lot of expertise, and we're really going to help and work with the WebRTC standards community to make video work fantastic for everybody. And we're going to go to SuperOp and things and do a lot of interoperability testing between the WebRTC browsers, the WebRTC endpoints, and the non-WebRTC world, which we've been focusing on so far, which is basically testing between WebRTC implementations and SIP implementations, so we can bring in, for instance, SIP-based video conferencing systems into WebRTC conferences like we have on Circuit today. Okay, next one. So I expect, like things like the IETF, for example, WebRTC will filter its way through a lot of other work in the IMTC. I mentioned a couple of groups here in the IMTC that are currently active and doing sort of work that's related to WebRTC. One is the SIP Interconnect Activity Group, very much focused on interoperability of SIP, and we in the WebRTC Activity Group work very closely with that group, which is chaired by Charles Eckel. I think he's on the call today. And we're working with them on looking at WebRTC interoperability with SIP. Another group, chaired by one of the speakers, Alex, is the IMTC Scalable and Simulcast Video Activity Group. I don't think I probably need to say very much about that because I think Alex will show some slides later. But obviously that has a lot of expertise in that group, which will help with the current operations in the current activities in IMTC, in IETF, etc. Yeah, so that's it. Thank you. Hopefully that was just a quick introduction to the IMTC WebRTC Activity Group. We hope to see you there. Hope to see you at SuperOp and contribute to help us make things work.
Yeah. So Andy, thanks a lot. Just quickly, 2 questions. So just in case, and I hope a lot of people are interested in getting together with you and maybe even joining the group. So what would be the procedure to do so?
Well, you can certainly find instructions on joining the group on the IMTC website, which is shown there. You could obviously follow us, directly ask me questions either on Twitter or email me or whatever. But there are instructions on the IMTC website.
Yeah, so I would highly encourage, in case you're not yet member of the group, go there. It's really interesting stuff. Another question I quickly have before we're turning over to Alex. You just quickly mentioned IMTC SuperOp 2016, right? Okay. So what can we expect? First of all, when will it take place? Secondly, what will happen in regards to WebRTC and why it definitely makes sense to join us there and figure out what's going on?
So it actually takes place in Orlando, I think around the 3rd week of May. I think it's around May the 16th, 20th, something like that. So in a nice hotel in Orlando. I expect we'll follow on from last year. We did quite a bit of WebRTC to SIP interoperability testing with WebRTC gateways, WebRTC enabled MCUs and endpoints, so we can bring SIP video conferencing systems, which might already exist in various enterprises, into WebRTC-based conferences like Circuit. We may well see, we're currently discussing in the group about the WebRTC scorecard and how we might actually test browser implementations and score them against each other, see where they're deficient. That's a little bit work in progress, but hopefully we'll get there.
Okay, cool. So, Andy, thanks a lot. I think questions from the whole auditory will be handled in the Q&A section. I would like to move over to Alex. And Alex, please share your view in regards to WebRTC evolution. Please go ahead.
Right, thank you. So I'm also a member of IMTC and other different groups, and I'm going to talk to you more about the historical evolution of WebRTC during 2015, because it changed a lot, and some people might still think about WebRTC the way it was back then, and I thought it was good to bring it up. Then a little bit later, Bernard is going to go through some of those details again, so I might go a little bit quickly, and you can keep your question for the end of the presentation after you've seen all the presenters, right? So the only 2015 model for WebRTC was a pure P2P model, where a web application running in a browser would be able to connect to itself running in possibly a different browser, going through a signaling channel. And then the browser will take care about almost everything, including encryption, media establishment, and so on and so forth. So the goal, the use case for that model was a one-to-one call. And the idea was to make it as simple as possible to use and that it would just work. So most of the work was delegated to the browser, and the application wouldn't have control about a lot of things. Next slide. So there were a few questions that we couldn't answer with that model, and that were communicated to the standard committee. How can I handle the bandwidth preference? Because I might know more about the network environment than the browser does. How can I check the fingerprints to avoid a man-in-the-middle attack? How can I handle codec and the parameters and so on and so forth? For those three questions, there were a few possible ways to try to make it happen, but it was not really stable, not documented, nor anything. And then there were some questions that just didn't have any answer, right? Can I handle which media path I'm using and which transport I'm using for the media? How can I restrict the information that I'm sending over the wire about my IP for security reasons, and so on and so forth. So we quickly bumped into limitation of that design. Next slide. So we went into the object model concept. So the object model is very simple. Instead of having a big black box called peer connection that does everything for you to make it simple, we're going to cut that into smaller objects, which would each have only one function, which could each be probed for capability from the JavaScript, and whose parameters could be set or get dynamically in JavaScript. So for example, if I want to change the bandwidth or the resolution or anything during the call, I don't have to stop the call and renegotiate. I would be able to do that directly. So that was inspired by the ORTC group. And Bernard is going to speak to you a little bit more in details about these diagrams here a little bit later. That allowed to answer a lot of questions. Next slide. So we've used some of the object models API concept into the WebRTC specification. So if you look at the WebRTC 1.0 specification today, you will see both the peer connection object and the object models, right? So now we have a final API to answer 6 of the original questions. Namely bandwidth preference, checking against man-in-the-middle attack, checking which transport is being used, getting more information about what it failed, if it failed, and having the possibility to do all of that without using SDP, GSEP, and so on. There are still a little bit of work to be done, but as you can see, most of the questions have either a final or a partial answer right now. Next slide. So the object model API was designed without SDP in mind. So when you wanted to bridge the gap between a pure object model and WebRTC, you had to add a small object called a transceiver to be able to map those objects to an SDP that then is going to be used for the handshake, the connection establishment. So that RTP transceiver that you see in blue here in the diagram will be the main difference between the WebRTC 1.0 spec and the pure original ORTC spec that Bernard is going to speak about. Next slide. And the main reason behind that is that SDP is increasingly bidirectional. So you cannot send only or receive only really in SDP. You have to find a way to have an object that reach the sender and the receiver model to map directly to an M media line in the SDP. So now your application can directly query the transceiver to get enough information to build or set the SDP and be compliant with the original WebRTC signaling part. Next slide. So eventually you end up with something like that. It's pretty much the ORTC model, but layout a little bit differently and with an additional RTP transceiver. Next slide. And if you wanted to start from an ORTC implementation and rebuild the WebRTC compliant shim, you will just have to put that big black box around here. And some people have already done that for audio, and the work for video is ongoing. Next slide. Now, to bridge with what the other Dr. Alex is going to speak to you just after, I want to speak a little bit about multi-party, simulcast, and SVC. Multi-party is about sending several tracks within the same connection, each of those tracks being understandable separately, right? And each of those tracks handling bandwidth management separately. That has been possible in WebRTC for years. Simulcast is a little bit different. You still have several tracks, but they're coming from the same source. They're still understandable separately. So even if you lose one, or if you get only one of those, you can view it, right? But you have the capacity to have a much smarter bandwidth management. Like if the bandwidth is going down, you might decide to shut down the high resolution stream and keep the low resolution stream, instead of trying to adapt the resolution for each of the free streams like the multi-party implementation would do. That simulcast is the biggest item, but recently in the WebRTC 1.0 spec, and we think it's going to make a big difference in 2016. So that refers to what Andy was saying before. We're expecting a lot of new things in WebRTC for video, and simulcast is definitely on top of that list. So just for reference, SVC encoding is the way to encode the video to increase the capacity of the simulcast. So you have several tracks, they're all coming from the same source, exactly like simulcast, but you're going to encode them in a smart way that does not let them be understandable separately, except for the base layer, but allow you for using less bandwidth, having a much better error correction, and so on and so forth. So again, I'm not going to go into the details here because Alex is going to speak about that in 2 minutes. This is a codec discussion and not an API discussion. So the Simulcast API that is in WebRTC 1.0 today, or almost, is going to be able to use this SVC codec when they will become available. Microsoft is already proposing an SVC codec, and VP9 should be SVC. So without further delay, I will let the other Dr. Alex speak a little bit more about that. Just a reminder, this is for a single connection. If you don't put all your streams and track in a single connection, then you cannot have the smart bandwidth management and everything we spoke about. All right? Yeah, I think I just passed that. Next. Yeah. Right. You can skip that slide.
Okay. So Alex, thanks a lot. Very interesting. I have a ton of questions from my end, but I don't want to screw you up right now. I want to give the other Alex and Bernard as well the opportunity to talk. So I just keep my questions for the end, and hopefully we get other questions from the participants as well. With that, I would like to turn over from Alex to Alex. And Alex, please take it from here.
Thank you so much. Good. So we're going to talk about how video is handled in WebRTC. And first of all, as you know, WebRTC is defined in two standardization worlds. One is in W3C and the other one is in the ITF. For video, I guess the most important component is not on the API side, which is W3C, but really on the ITF side. And the requirements for that are described in this internet draft ITF RTC web video. Latest version is from June, and it's a very short one, 9 pages, and it defines the requirements for the video codec and transport. From the API side, as the other Alex said, pretty much the video is handled as a black box. It's just use it and it sort of works. So this specification defines the requirements that are necessary for the video codec. And they're actually surprisingly few. First of all, you have to be able to deal both with camera input, but also screen content, capturing content from your computer screen. So as a result, you have to be able to expect midstream resolution changes. You may also have support for mobile devices where they can have different video orientations, and there is specification on how to do that using the coordination of video orientation mechanism. And finally, what's specified in terms of the color space and the chroma format is luminance versus chrominances in the 4:0 chroma format, which is not ideal for screen content, but works very well for regular video. But just don't expect to be wonderful, for screen content that requires very high large number of bits per pixel, and typically it's RGB in a 4:4 chroma format. Next. So one key issue with video in WebRTC was which codec to use, okay? And this was a very big discussion that lasted for a very long time, okay, on how to deal with this mandatory to implement decision. And it was decided in November of 2014 that the mandatory to implement codec would not be one, but two. So it will be VP8 and H.264 constraint baseline. And in fact, browsers are supposed to implement both. But WebRTC implementations that are not in browsers, okay, must implement both unless one is declared royalty-free, in which case it should be the one that people have to use, okay? And the argument, again, between those two codecs is, relative efficiency versus the necessity of paying, royalties for use. So with respect to VP8, okay, you have to support the VP8 RTB payload format, which is in draft status, and conform to maximum frame rate and some related TP attributes. For H.264, you have to support the corresponding, again, RTP payload format, which is RFC 6184, in the constraint baseline profile, which is very commonly used in old-style video conferencing systems at level 1.2, which is like 240 pixels to 240 lines. And ideally, you should support a constraint high profile, better coding efficiency at the level 1.3, which has similar resolution. And you support a non-interleaved packetization, which is great. That's the most modern way to use 264. And you have send information in band, not using SDP. So that's the basic. These are the basic requirements. You can go to the next one. So if you look at an application that uses video, and this tries to capture the prototypical environment, you have in the white box, you have a core WebRTC engine. On top of that, you probably have some sort of JavaScript library that makes it easy to develop applications that exposes some sort of JavaScript API. And then on top of that, you write your own code. That's the yellow box, okay? And then you have an application running on a server, right? And there's signaling that you designed to talk, for these two to talk to each other, okay? So if you want to do point-to-point calls, if you can go to the next slide, if you want to do point-to-point calls, fine, both browsers may speak to the same portal or not. But bottom line is that the media will flow directly from one browser to another. No magic here, we hope that the codec will do what's necessary to make this happen. When you go to multi-point, things start to get a little bit more interesting. So if you go to 3 participants, the natural thing to do is to create a mesh where every participant transmits video and audio and data to both of the other participants, right? And this sort of kind of works if you have just 3, as in this example. But if you go, let's say, to 4 in the next slide, you start realizing that the overhead in transmitting data from each endpoint starts to become very significant, okay? And bandwidth is an issue, not traversal is another issue. So this quickly gets out of hand, okay? So this is a problem, by the way, that's very well known in the video conferencing industry for many years. And the way to solve it typically is to actually use a server in the middle. So if you go to the next slide, right, what you probably want to do is have some entity in the center, right, and everybody transmits to that entity, right, and that entity decides, what to transmit back to the participants, okay? So I want to explore a little bit what that red sort of thing in the middle may be, okay? And in the process, I will be depicting video streams, and I will do so using these, yellow strips. Okay, these are the video streams, and there is an associated icon to identify this as a, as a video, okay? So the simplest way to do that, the server, is to use what's called a switching MCU. In the next slide, MCU standing for multi-point control unit, where the server basically receives multiple streams, here are 4, and decides which one to send to the receiving participant. In this instance, only the B participant was selected. It's very simple to do, very low processing, very low delay, but you can only see one person at a time. In the mixing MCU, which is the next slide, you use a trick that's available with some codecs, good, thank you, where you can actually receive low-resolution images and then copy-paste them as components of a larger image without decoding or processing in any shape or form. So you can see here that all 4 participants were copy-pasted in a large image, okay? Again, this is very simple, no signal processing, okay? But you are limited, if you can go to the next click, you are limited in that, no, go back, sorry. One click at a time, sorry, yes, thank you. One click back again, back. Thank you, good. So you are limited in the layout, and of course you cannot see anybody in high resolution because the inputs are low resolution to begin with, okay? There is some delay, but very little, okay? And again, you require special support from the codec, and the last one that supported that was 261 in a commercially available profile. More recent ones, we know in theory they support them, not in the profiles that have been adopted. Let's go to the next slide, which describes the transcoding MCU, and that's kind of the industry standard. Has been the industry standard until about 2008. And the idea here is that you receive coded video, you decode everything, you compose it, and you re-encode the result to transmit to the receiving participant. So if you can click once more, thank you, yes. So this is very flexible, but it has very high delay, typically 150 milliseconds and up from input to output, and you also have transcoding loss, okay? So because of the cascaded decoding and re-encoding, the quality suffers. So this is very complex. This requires a lot of signal processing. And again, even if you ignore the cost of processing, the high delay is very problematic because it impacts how natural the interaction is among the participants. Okay. However, this has been the standard way to do multi-point video for many, many years. And in fact, if you can go to the next slide, if you look at the RTB topologies RFC, which is 5117, it is recognized as this, the top RTCP terminating MCU, and that's it. That's how things have been going until 2008. So what happened next, if we can go to the next slide, is scalable video coding was introduced actually by video as a way to get around this problem and introduce a new architecture. So as Alex G mentioned, in scalable coding, you create video starting from a camera source or from a source to the pyramid process, where you have a low resolution version created as the base, and on top of that you add information in the form of an enhancement layer, okay, which adds additional fidelity to the signal. And this can be in terms of frame rate, it can be in terms of spatial resolution, okay. In this diagrams, I'm just showing 2 layers, a base and an enhancement, but you can have more than 2, okay. So I'm going to be showing scalable things like that. Now, this has some overhead versus single layer coding, but it's much more robust to the point of 20% packet loss rate. Again, I'm not going to go into detail of how, but that's a huge advantage. And of course, you get adaptation because you can use a subset of the layers to obtain a version of the signal at different fidelity point. Okay, so why do you use that? So one is robustness. The second is because we want to introduce a new architecture. If we can go to the next slide, which we have called the video router, where the server now receives scalable coded streams, and what it does is it selectively forwards packets from each layer to a receiving participant. So you can see in this example, the server transmitted full resolution for participant B, so both the small b and capital B layers were transmitted, base and enhancement, whereas only the low resolution versions were transmitted for A and C, okay? Why? Maybe there was not enough bitrate, or there was not enough screen real estate to display, or maybe B was the active participant and you wanted to see them in high resolution. Regardless of the reason, this is just purely a forwarding decision that is made by the video router. There's no signal processing that has to take place to affect this kind of operation. So this is extremely low delay. In practice, this takes less than 10 milliseconds input to output. Okay, so you can see that you know it does wonders in terms of making the interactive experience for the end users basically transparent. And if you look at the endpoint, if you can go to the next slide, the endpoint architecture is very interesting because now the endpoint is multi-stream. Okay, so it has to receive multiple video streams and audio streams, by the way, and it has to decode them and do the composition in the endpoint. And this is very similar to a web browser, right? The web browser fetches content, and it's a browser that does all the rendering and the positioning and information on the screen. Okay, and so even though this was introduced, many years before WebRTC was introduced, it actually matches WebRTC in a perfect way. That's exactly how a WebRTC client works. You can click one more. All right. Thanks. Yes. So this is very important because you can see that by being able to manipulate things on the endpoint, on the WebRTC endpoint, what you want to do is also have a corresponding server that can similarly manipulate streams individually. Okay. So that's how the server works when you have scalable coding. You can do something similar with simulcasting. So with simulcasting, as Alex G said, you do multiple encodings of the same content at different fidelity points or different resolutions, for example. Here I'm showing two distinct resolutions for participant A, okay, small a and capital A. Two distinct streams, two separate encodings, both of which can be independently decoded by a receiver. You don't need the other to operate. So how does the server work in this case? If you can go to the next slide, we transmit both of those streams. Oh, by the way, yeah, so the overhead with Scalable versus Simulcast of Simulcast versus Scalable is non-trivial, okay? In the order of 50% versus single layer for Simulcast and maybe 20 for Scalable. So you can pay a steeper price for that. Now, how does the server work? Well, we transmit both layers to the server, and the server will select which stream to forward, okay? So it's more expensive, if we can click one more time, it's more expensive on the uplink, right, because you spend more bits. It's lesser resilience, and you do two encodings. On the other hand, it's appealing if you have legacy decoders because all the streams, all the layers, if you wish, are individually decodable. And it may also avoid trusting the server, okay? So if you want to do end-to-end encryption, okay? So go to the next slide. So we have actually, next slide, please. So this is actually used today, okay, in commercial system by video, obviously, by Google Hangouts, by Microsoft, okay? So this is something that has been deployed, okay? So this is the way to go when you do multi-point video and you want to get high quality. And in fact, we have introduced, if you can go to the next slide, we have introduced a term for this, actually coined the term back in October 2013, selective forwarding unit, right, as a term to use for servers that have this architecture. So regardless if you use scalable coding or simulcast, right, the operation of the server is pretty much the same, all right? And this is now captured in an update of the RS-50 117, which hopefully will soon replace it, all right? So I think that's really cool. Now, going one slide next, please. So scalability has been a feature of 264, obviously, and actually 265, HEVC, but we have been working with Google to actually introduce scalability in VP9, which is a much better codec than VP8. It's not mandatory to implement, but it's certainly the next generation codec. So we added that scalability. We also created the RTP format and also developed the code for it. The first release is already available on Chrome 48. Which came out in January. The receiver is fully supports scalability, so you have backwards compatibility with future versions of Chrome. The sender, however, requires API support. So right now, the VP9 codec that you would use, the encoder, would not use the scalable features, okay? The ORTC API, as Bernard will talk about later, does support spatial and temporal scalability, but it's not there yet for WebRTC 1.0. We just recently completed the detailed performance analysis for Scalable VP9, and the results were great. I cannot share them right now. Hopefully, I will do so soon in another venue, but they were extremely satisfying in terms of comparing the relative performance of scalability with Simulcast for VP9, 264, and 265, okay? And finally, and with that I'll close, all this work on scalable coding is addressed within IMTC in the Simulcast and Scalable Video Activity Group. If you can go to the next slide. Thank you. So I'm co-chairing that group with Jesus Pedro from Polcom and Gal Eliraz Levonai from Avaya, and that's where we address the use of scalable coding and simulcasting on the victim level and on the transport level. Okay, I'm over my time. Thank you very much, and I'll be happy to answer questions at the end, I guess, when we have a Q&A. Thank you very much.
Thanks, Alex. And with that, I want to turn it over to Bernard, quickly bringing up his presentation. And Bernard, the stage is yours. Please go ahead.
Okay, thanks, John. So this is a presentation put together by myself, Peter Thatcher of Google, and Raman Raymond on the status of object models. Next slide. So I guess the first question is, why did we need to do all this work to put the object model into WebRTC 1.0? So the motivation came from a couple of issues that we have. One was that we wanted to be able to tweak parameters of individual tracks. So in STP, for example, we have bandwidth attributes, but they relate to the capabilities of the receiver. So for example, you can indicate how much bandwidth you're able to receive or the maximum frame rate that you're able to receive for a given codec. But that doesn't relate to the actual bit rate that is sent or the actual frame rate that an encoder is sending. So there's this little missing attribute. Now, in terms of directions, in offer answer, we can also negotiate send only, send receive, receive only in active states. But that doesn't necessarily tell you at any given moment whether you're sending or receiving, whether the encoder or decoder are actually on. So slight difference there between the capabilities that you would have in an object model and STP. Now, the existing APIs within WebRTC 1.0, create offer, did not give you this per track control. And similarly, with AddStream, you couldn't modify things once you added them. Now, we, of course, did have media stream constraints within Get User Media, but that didn't affect the encoder. So there are a couple of little missing pieces that we had within Peer Connection that we wanted to get, and I'll talk about some of the use cases that we wanted to enable. Next slide. So what's the difference between the WebRTC 1.0 object model and ORTC? So the objects are themselves the same. So if you go into the WebRTC spec, section 5, which we're working on now, you'll see that 80% of all the objects in ORTC are now in WebRTC. Many of the attributes, the methods, they're all the same methods. So what's the difference now? Well, the difference is that in WebRTC 1.0, most of the attributes are read-only. That is, you create the STP, you do the negotiation, and you get back objects. But in most cases, you can't set the attributes. There are a few attributes you can set, which I'll talk about. Also, there are attributes which, if you set them, they will cause a renegotiation. Whereas in ORTC, there is no STP, and so you can control things directly, and you're actually able to set all the non-read-only attributes. So that's the major difference. The objects themselves are very similar. Next. Okay, so a little bit about the project and converging these things. So we now have in section 5 of WebRTC 1.0, which has all the objects, so the basic things are in there. We've actually implemented ORTC within Edge, so we have some real code out there as well. We've done some work recently in converging the ICE state machines in both specs, and those are going to be fairly identical pretty soon. You'll see a lot of changes going into the ICE state machine and the ICE state definitions within WebRTC 1.0. We actually have successfully emulated Peer Connection in ORTC as well, which is kind of one of the promises of ORTC, which is that we could implement 1.0 on top of it. Also, Google has started implementing the WebRTC object model as well as ORTC. You may have seen the basic sender receiver already in there for mobile apps. There's more to come in 2016. Hopefully, we will get to the point where the object model is solid enough in 1.0 for implementation to begin. I know actually Mozilla already has a bunch of it in there as well right now, and eventually it'll be available everywhere. Next. Okay, so a little bit of the differences. A year ago, basically, you had an application talking exclusively to Peer Connection with the objects hidden underneath, only visible through the statistics, and only indirect control. Next. And now you see the objects in section 5.5, and this includes ICE, CTLS, SCTP, and RTP. related objects. Again, same ones as in ORTC. Next. Okay, so here's the ORTC in a little bit more detail. We have a pretty big update to the spec that came out on March 1st. Basically, the only objects that are here that aren't in 1.0 is a few things. We have what's called a separate ICE gatherer in ORTC, and this was separated out from the ICE transport in order to enable forking. But in 1.0, the ICE gatherer and the transport are combined. We also have something called the ICE transport controller in ORTC. We did not implement this in Edge, but the basic idea of this is to emulate the ordering of the ICE transports that you get through SDP. And then the last object, which is in ORTC but not in WebRTC, is something called the RTP listener. And this is something that exists to make an application aware of a stream that it didn't expect. So something that doesn't match the parameters. We had similar discussions with relating to SDP, what happens if you get them. And there's still some questions about this object, whether it's really useful, because when you get this event that tells you you have a stream that you didn't expect, well, if you didn't expect it, it's not always clear what to do with it, right? You don't know whether to render it or unless your application really has a good idea of what's coming in. Next. Okay, so here are all the additions to the WebRTC 1.0 spec. Quite a few new methods and attributes. And let me just basically give you an idea what's going in. So in the sender and receiver, we now have the ability to get capabilities. That tells us things like the supported codecs. And we also can get the parameters. So as an example, we can do the SDP offer answer, get back the parameters, and then potentially change a few things in set parameters. You'll notice that set parameters only exist for the RTP sender, but not the receiver. And that is intentional because there's really not a lot you can set in the receiver other than potentially the active state, whether the coder is on or off. Most of the parameters that exist for the sender don't make sense for the receiver. So we've pretty much left that out. We have a new method called get contributing sources for the receiver, which give you information on the CSRCs in a conference, also the audio levels and things like that, help you build a UI that give you an idea who's speaking. We have the ability in the sender now to change the track. So for example, we could go from a front-facing camera to a back-facing camera with replace track. We have pointers. These are read-only to the transports, the DTLS transports that the senders and receivers are using. And in the DTLS transport itself, we have information on the individual state of the DTLS transports, on the certificates, which come from get remote certificates, and a lot of details also on the state of each individual ICE transport. And you'll be seeing more info coming into the spec in the coming weeks. Similarly for SCTP and the data channel, these are really more read-only objects in 1.0, give you a lot of information on the state of the SCTP or data channel. We have something called RTP parameters. This is really what tells the encoder what to do. It includes information on the codecs, which come out of the SDP offer answer, and also information on the encodings. And an example of this is the setup for Simulcast. I won't go into detail on all these things, except for some of the new knobs that we added in 1.0. I mentioned the active parameter, which tells you whether the encoder and decoder are on or off. We have max bit rate, which tell you the maximum bit rate to send. Max frame rate, which tell you the maximum frame rate to send. The RID, which is useful for Simulcast, which is currently read-only. That it actually is set in the add transceiver initialization, but you can change it after it's been negotiated. Resolution scale down by, this is really a Simulcast attribute that allows you to scale the incoming track. And then the SSRC, which is assigned by the browser, which is read-only. Next. So what can you do with all these new toys that you have? Well, a couple of use cases we're trying to solve, and hopefully we'll give you the detail in the spec as to how this all works. You can warm up a media path while getting a track and ringing, and then that means putting all the transports in place so you can get media. You can change the send codec. As we know in offer answer, you can offer multiple codecs and even answer with multiple codecs. But then you can also, once that happens, the object model allows you to change the order. So you could move, for example, from Opus to G711 or back or something like that in the middle. You can change the camera source. I mentioned replace track. You can enable and disable the sending of media instantly. For example, you could turn the encoder off or turn it on. You could turn the receiver, the decoder on or off. You got to be a little careful because make sure the other side, you got to signal that and offer answer most of the time, so the other side is willing to adapt to that change. But you can do it instantly. I mentioned the maximum bit rate or frame rate, and then you get a lot more information on the status of the individual ICE, DTLS transports, and then you also can send simulcast now in 1.0. Next. So what can you do in ORTC but not in WebRTC? Well, I mentioned you can configure the objects without any SDP. Also, ORTC supports scalable video coding, and let me talk about this. Scalable video coding is actually supported today in 2 browsers. Chrome supports VP8 temporal scalability. As Alex mentioned, the code is there to support VP9 temporal and spatial, not turned on at the moment. And Edge has supported H.264 SVC, both simulcast and temporal scalability. So 2 browsers already do this, but they do it basically in the codec, kind of under the covers. In Chrome, there's just a few things you do in the SDP to turn on both temporal scalability and simulcast. They both go on at the same time. In Edge, it's very similar. When you negotiate the H.264 UC codec, basically you get simulcast and scalable video coding automatically. But what we're trying to do in 1.0 and in ORTC is to give the developer detailed control.
SDP portal est toujours utilisé ou pas pour réserver le congé? Parce que je pas
the other thing that we have, could you mute, please? The other thing is that we do allow in ORTC is...
Somebody speaking, please mute.
Yeah, I muted the guy, so sorry for that.
Yeah, the other thing you can do is call forking. This is enabled by the ICE gather and also some forking capability that was added to the DTLS transport in ORTC, which requires the certificate management API. And I mentioned the RTP on handle event, which in my opinion have a questionable usefulness, but next. Okay. So what can you do now with ORTC to play around with it? Well, you can use it in Edge. You can write native apps. You can also use adapter.js to run the existing WebRTC 1.0 code on top. Next. And currently, if you look at adapter.js, it has the shim capability built in. There was a pull request 136 that's now merged that enables this. And so if you go to the WebRTC audio sample page, you can basically run those apps on Edge. Video doesn't work because we don't have the H.264 AVC codec yet, so we don't have video interop, but the audio samples already work. Next. Okay, so you can play around with these apps and see how they're built. We have 2 of them up on our website, Twilio, which has their own version of adapter.js, and then Simple WebRTC, which is built with the release adapter.js shim. So those are 1.0 apps running on ORTC. And then we have a native ORTC demo with the H.264 SVC codec up there as well, so you can try these. Next. Okay, so here's a little bit of code talking about some of the examples. We mentioned a warm-up example. So you basically call pc.add transceiver, which gives you a sender and receiver for audio. You create another one for video, and then you can basically render the audio and video tracks, hook them up, and then you can replace track and put on another audio track or another video track to send. Now, it's a little bit more complicated in ORTC, but it's basically pretty much the same code. You create your senders and receivers for both audio and video, and then you can also use set track in this case to change the inputs. Next. This is a change camera example. Looks pretty much the same in WebRTC and ORTC. You basically call replace track to replace the camera. Maybe go from a front to a back or the other way around. Next. Sending codecs is pretty easy either way. In WebRTC, you call get parameters, you reorder the codecs, and then call set parameters. In ORTC, you basically call sender.get capabilities, change things, and then call sender.send. Next. The maximum bit rate is pretty simple as well. In WebRTC, you call get parameters, you change the max bit rate, and then you call set parameters. And in ORTC, you basically set the max bit rate and call send. Enabling or disabling, in the WebRTC example, you're calling get parameters and then setting active to false, and calling set parameters to set it off. And then you can set it back to true and call set parameters again. In an ORTC, you just call sender.send with a value of false or true. One thing I would note about this that people should understand is, as an example, when you turn on the active to true again and start sending to somebody else, it may make sense to do an offer-answer negotiation, because they may not have been expecting your video, because as an example, you might have been receive only and they were send only, right? So they were sending to you, not the other way around. If you just start sending to them, if their decoder is off, it won't do anything. So this actually might make more sense to trigger offer-answer unless they were already expecting you to send. Next. This is a simulcast example. We don't quite have everything done for either ORTC or WebRTC for that matter, but the basic parameters are max frame rate and the resolution scale down by, called resolution scale in ORTC. And so here you call sender.send, and this would be sending 3 simulcasts at full 1/2 and 1/4 resolution. You can more or less do the same thing in WebRTC 1.0, but we do have a few little things to do to make that possible. Next. Okay, so I'll just talk for a wee bit about what's in Edge. As I mentioned, we have all the objects that are in 1.0, and basically the things that we didn't put in aren't in 1.0. Next. We basically have the full complement of audio codecs. For video, we have this H.264 SVC implementation, and we have a forward error correction, which actually is pretty sophisticated because it can handle burst loss. And we also have did the statistics stuff, plus an additional MS Stats API, which has a lot of supplemental information on things like burst loss and forward error correction quality, stuff like that. We handle both bundle and RTP, RTC MUX, IPv4, IPv6, all that. Next. There are some limitations. One of the biggest ones is no data channel. We also have no forking support at the moment. And there's some things with ICE that are missing. We don't handle SSRC conflicts. And one of the bigger ones is we don't currently support DTLS 1.2 and ECDSA, but we're working on it. Next. I'll just, next slide, just talk one thing about the roadmap. Just go to the next slide. Yeah, so a couple of things coming down the pike. We're considering media recorder and screen capture. Those are pretty high probability that we'll implement those, but waiting for the specs to firm up a little bit. We support the VP9 codec, but only for streaming media. This isn't hooked up to ORTC yet. We do support ORTC, as I mentioned, are looking into improved WebRTC 1.0 compatibility, and we'll see how that works. As I mentioned, we have adapter.js already, but we've had some folks point out bugs and various little incompatibilities, so we're going to continue working on that to get better 1.0 support. Next. And here's some basic information so you can find out more. We have the Windows Insider Preview program. If you sign up for that, you'll get all the newest Edge builds, and you can play around with new stuff that we'll be working on in 2016. And that's it for me.
Thanks a lot, Bernard. Really comprehensive material, super interesting for me, hopefully for everybody else as well. So with that, I would like to turn into the Q&A section. And please, as I told you at the beginning, you can unmute yourself to ask questions by either using the unmute icon in the client, or in case you were dialing in, pushing *3 in order to unmute you on the phone. So, are there questions, comments? Okay, maybe you still think about that. I have some questions here on my end, at least. And I probably start with Alex Bouillard, okay? So you were talking about the status of the implementation. So as I'm a guy with a lot of Apple devices, I'm of course interested in what can I do in regards to WebRTC with Apple, with Safari, with my iOS devices. Can you help me with that?
I wish I had that power. I can give you some information, but that's about it. The state of the art is that Safari and WebView on iOS are not supporting WebRTC yet. Now, Safari Nightly, which is built every day and made available for everybody at webkit.org, has some WebRTC API implementation. So it's very likely that by the end of the year, when they release the new operating system, we will have WebRTC in part or as a whole. It looks like they implemented WebRTC 1.0. So the sender, the receiver, and all of that, and not ORTC. And I don't know what they're going to do for the codecs. So the situation is right now, nothing you can do. You can go native. It always works.
Mm-hmm.
But by the end of the year, we should have something in the official Safari build.
Okay, cool. Thanks. And not sure whom I should ask that question, but I saw it a couple of times. You were talking about SVC codecs. That sounds really interesting. So what's the status there in regards to implementation and in regards to coverage by browsers and different solutions?
Well, I think video is helping Google doing the implementation there. So maybe Dr. Alex E. can give you more detail. But I think that Firefox and Chrome have some implementation of VP9 today. I do not know if it supports SVC yet. Alex?
No, we did cover that already. So I said that Chrome 48 already contains scalability in VP9. It will work on the receive side. The encoder piece is not activated yet, even though the code is there. So if you go to the WebM repository or the WebRTC repository, you'll find all the scalability code. But the way it's incorporated into Chrome and the APIs available to use it do not allow you to exercise this on the encoding portion, okay?
Okay, so if I download Chrome, it will not work, but if I recompile code, I can actually enable it. That's
right. It will work. Look, it will work with VP9 without scalability, right? So you can still use VP9 today, just not with those features. And as Bernard said, for Edge, VP9 support right now is for streaming applications. It's not available yet for real time, okay?
Yeah, but also Chrome supports VPA temporal scalability today. It can be
Correct.
turned on in the encoder.
Correct. Yes. Thank you. Yes.
As I understood it, Mozilla does not allow Mozilla can decode temporal scalability in VP8, but it can't encode it.
Okay. Then
it can use scalability in 8.264 though, Mozilla.
Oh, really? Oh, I didn't know that.
Yeah.
Okay.
Okay, guys, let me quickly check with our other participants whether there are people having questions. I see most of you are still muted, so either you did not make it yet to unmute yourself, or you don't have questions. So please speak up if there are. If not, for the time being, you might still think about the one or the other question. I have another question in regards to, so Alex E., you were mentioning a so-called SFU. And so that seemed to me it's something which is just coming up. I remember when WebRTC was going to get more popular, we were always talking about security and how important security is. But yeah, what is the status in regards to security in combination with an SFU environment?
That's a good question. So the way the SFU works typically is by actually examining the payload to figure out what its packet contains. As a result, until today, the SFU has had to be in the security context. So it has to be able to decrypt the content. There is, if you use simulcasting, things are a little bit better because you don't need to necessarily to look at the payload to figure out, what is what. Now, because of the significance of this feature, if you wish, in the post-Snowden, era, there is actually an activity in the ITF called PERC, Privacy Enhanced Real-Time Communication, which examines this very issue. And the idea there is to be able to do sort of like 2 layers of encryption. One is end-to-end, the other one is like hop by hop. So you don't compromise the media, right? But you can still have whatever information is necessary to do any intermediate processing. Okay. I know Bernard is also following this. So this is something I think that will be available soon in most systems. Okay.
Okay, cool. Thanks a lot for the answer. Again, checking with the auditory, any questions from our participants?
Andy here. I had a question for Bernard, actually. I think it's a reasonably straightforward one.
Go ahead, Andy.
So we talked about, the video implementation work you still have to do for Edge. What about the screen share? Do we get that automatically once you've done the video work, or what's the status of screen share?
Yeah, so basically we've indicated that screen share is under consideration. That is a separate W3C screen sharing spec that's currently under development. So once that's ready, we will implement that. It's different from Get User Media, and that's our plan. And that will basically run with any video codec we support. So you basically you produce a track from the screen sharing API. It's called Get Display Media instead of Get User Media, and then you can encode that track with any video codec that you have in the system.
So the status is it's under consideration at the moment.
It's pending basically the spec getting to a little bit more finished state, but we put it out. It's basically high probability of implementation, but we can't basically develop it yet because the spec isn't quite finished.
Okay, thank you.
Thank you. Bernard, I have a question for you as well. So there are probably a lot of people asking whether the WebRTC.org source code has been ported to WinRT. Can you give us a kind of information on that?
Yes. So if you search for something NuGet, N-U-G-E-T, WebRTC, you will find a WinRT package. So that is, you actually can develop WebRTC apps on WinRT. Also, you will notice that ORTC Live, in the slides that I didn't present but are available, is also available for WinRT. So basically, and those work with the existing tools, such as Visual Studio, and so you can develop apps on WinRT for both WebRTC APIs, or if you prefer the ORTC API.
Okay, cool. So then my last try to the auditory. Any questions? Don't be shy. Come on. If not, and there are always ways to get in contact with us. It's quite easy. Go to the IMTC.org page /contact. Get in contact with us. Get in contact with the people here on the call, with all the presenters. Follow us at IMTC.org on Twitter and get in contact with us. That would be the easiest way. Before finishing, I have a very last question to all the presenters. What would be your top #1 item you would wish to accomplish in the coming year in regards to WebRTC? I would love to go around, Andy, Alex, Bernard. So please, just a few words. But what if there would be an ideal situation, what would you like to wish to get accomplished?
I guess from my point of view, getting the WebRTC 1.0 work finished in the W3C, I think, and then really, trying to get browser implementations which are conformant to that. Hopefully by the end of the year, we're pretty much there.
Okay. Alex?
from my point of view, I think Andrew said it for the standard committee side. For the implementation side, I think we need more interoperability between the browsers, both on the JavaScript API and on the wire. And what's missing today is maybe a little bit more testing. And I think I'm going to spend time this year to work with the browser vendors to improve the tests available to help them reach that level. Because we can all help the browser vendors. We don't have to wait for them to do all the work.
Mm-hmm. Yeah, we certainly hope that IMTC SuperOp and things can either this year or even next year, whatever, can be a venue to help that happen.
Thank you, Alex.
Yeah, I think supporting browsers is key, because that's I think that's a fundamental assumption in WebRTC. And of course, for me, I think scalability VP9 would be great, because that's the only way to get very high quality from these browsers.
Thank you, Bernard.
Well, I would say video interoperability is a very high item, because a lot of the new work is really created for that purpose. So, I mean, starting with H.264 just one-to-one, and then going to multi-stream, and hopefully toward the end of the year, some of the simulcast scenarios, and actually getting those things to work and interoperate. Because until we do that, we won't have validated particularly all the new API stuff. So we really, getting all the tests to do that is actually a significant amount of work, because the test cases we have right now don't cover all of that.
Okay, thanks a lot. So my personal wish for the coming year in regards to WebRTC is that we have a lot of participants at our 2016 SuperOp, where we talk about WebRTC, but also test, right? So this is about interoperability. So I would love to see you all there. It's easy going. Just go to our website, go to the IMTC SuperOp 2016 subpage, and register there. With that, I would like to finish the call. Thanks a lot for your attendance. We are interested in your feedback, so please get in contact with us on all the channels. Looking forward, and coming up pretty soon with another webinar talking about other great topics. Thanks a lot, and see you soon. Talk to you soon. Bye.
Thank you.